Cannot start video. Uh-oh. Hold on. Select another video. Okay. All right. Okay, hold on just a minute here. Okay. All right. Somehow the video is not recording, but I'm going to go ahead and share my screen. Okay. Go to chapter 8. Okay, those of you on Zoom, can you see the screen?
Yeah.
Okay, good. Okay, we have just a couple topics left from this chapter. All right, I sent out a message about labs. Okay, we're going to postpone spectroscopy until just before Thanksgiving, and the labs that were scheduled then will be moved to an earlier time. So this week we will be doing epoxidation of cholesterol. It's from the Williamson textbook. Okay, so here is epoxidation. It uses a peroxy acid. In lab this week, we'll be using metachloroperoxybenzoic acid, or MCPBA. And cholesterol, as we saw last week, it has a double bond. And so we're going to form the epoxide using MCPBA. Okay, this is similar to an oxidation reaction that takes place in the body, except the body doesn't use MCPBA, it uses oxidative enzymes. But oxidation, epoxidation is an important metabolic process. Right, this is the mechanism of epoxidation. It's a concerted reaction, which means that several steps occur at the same time. And so the transition state is cyclic like this. And we end up with an epoxide, and our byproduct is the regular carboxylic acid. In our case, it would be 3-chloro-benzoic acid. Okay, here's MCPBA, and then here is 3-chloro-benzoic acid. Okay, it's missing one of the oxygens. Epoxide rings are easily opened because they're under strain. This process can be acid or base catalyzed. We'll talk about acid catalyzed in this chapter. First, you have a protonation that occurs on the oxygen. Water attacks, and then water removes one of these extra protons. And we get an anti or trans diol. Okay, and the reason is water has to attack from the backside there in the second step. Okay, there are other reagents that are used for epoxidation, such as peroxyacetic acid. Okay, that doesn't allow you to isolate the epoxide like MCPBA does. There's also one called MMPP, which is described in your textbook. That's more water soluble than MCPBA. All right, we talked about oxidative, well, actually, we talked about syn hydroxylation. Okay, this is anti-dihydroxylation. Okay, the two OH groups are added opposite or anti to each other. Okay, we have two methods of doing syn hydroxylation. They are osmium tetroxide and hydrogen peroxide, or cold dilute KMnO4 in basic solution. Okay, these will both give you the cis diol. Okay, and the reason it goes through either an osmate ester or a manganate ester, both the CO bonds are added to the same face. Okay, and then just to review, we talked about some oxidative cleavage reactions where the carbon-carbon bond actually splits. Okay, if we use cold, dilute, alkaline, or basic KMnO4, we get the glycol. But if it's warm and concentrated, the carbon-carbon bond actually splits, and we get ketones or carboxylic acids, depending on whether we have hydrogens or carbons attached to the double bond. Okay, aldehydes are not isolated because they're immediately oxidized to carboxylic acids. Okay, so we split the double bond, we replace the CC double bond with two CO double bonds. Okay, in this one we have two H's, so we split this double bond, we split this double bond. The single carbon becomes CO2. We split this, since we have two H's, both of those carbons end up becoming carboxylic acids. All right, ozonolysis, again, splits an alkene. But if we use a reductive second step, okay, either zinc or dimethyl sulfide, then we can isolate the aldehyde. Okay, the aldehyde is not further oxidized to the carboxylic acid. All right, so double bond is split. Okay, one oxygen goes here, one goes here, one goes with the sulfur. Or if we're using zinc, we would get zinc oxide ZNO. Okay, the intermediate is not isolated because it's so unstable, so it's immediately reduced. Okay, so here's the main difference, and that is that whenever we have H's attached to the alkene group, they get oxidized to carboxylic acids with permanganate. They get oxidized to aldehydes with ozonolysis. Okay, when we left off, we were talking about polymerization. At the very end of the course in the spring semester, we will have a whole chapter on polymerization. But very briefly, alkenes are starting materials for what is called addition polymerization, where all the monomer units are the same. And there's three main methods of polymerization: cationic, free radical, anionic. Right, so if we start out, say, with isobutylene, with a strong acid like sulfuric acid, okay, rich get richer, so CH2 picks up a proton, we get the tert-butyl ion, and another unprotonated alkene then attacks. We get another cation, and then another alkene attacks that, and then the chain keeps growing. Okay, termination occurs when there's either an elimination or two chains link up. BF3 is another catalyst besides sulfuric acid that's used to initiate cationic polymerization. Free radical polymerization is commonly used industrially, particularly with polyethylene and polystyrene. Okay, we break an peroxide into two alkoxy radicals. Okay, these split up the pi bond to produce a free radical. The free radical attacks another molecule of alkene, which generates another free radical. Another alkene attacks that, and then the chain grows. The most common application of anionic polymerization is in superglue. When superglue hardens, that's a polymerization reaction. Anionic polymerization is much less common than the other two. In this case, we have two strongly electron withdrawing groups, the nitrile and the ester, okay, both of which can stabilize its negative charge by resonance. Okay, this anion then attacks another monomer, which generates another anion that attacks another monomer, and the chain grows. Okay, so all you need for superglue to harden is just a little bit of moisture, which will produce a trace of hydroxide ions, which will initiate the hardening of the superglue. Okay, we didn't talk about this last time. This is olefin metathesis. Okay, and basically what this involves is you use a special catalyst, and okay, we've got these two different alkenes. They have different substituents. Okay, we split the two alkenes, and then we add one part to the other alkene, and so we get something like this, cis and trans. All right, so this part then adds to this part, and this part adds to this part. We'll get two different alkenes. Okay, so olefin metathesis, okay, remember olefin is another name for alkene, is any reaction that trades or interchanges alkylidene groups. Okay, so here's an example. They use using a special catalyst. You split this. Oops. Go back. We'll split this, and okay, there's two of these, and so two of these CH2 groups will join to form ethylene, and then two of these groups then will join to form cis and trans 2-butene. These are a couple of the catalysts that are used, the Schrock and the Gibbs, or I'm sorry, not the Gibbs, the Grubbs catalyst. Okay, some more examples of cross and ring closing and ring opening metathesis. Okay, this is back here. This was, I guess you call it ordinary metathesis. Here's cross metathesis. Okay, where we have two different alkenes. We split them and then we interchange the groups. Here's ring closing metathesis. Okay, we split it here, we split it here, we close the ring, and then the other product is ethylene. And then this is ring opening metathesis, which produces a polymer. Okay, so the mechanism involves the metal alkylidine catalyst, forms an intermediate 4-membered ring with an alkylidine followed by ring opening. Okay, and then, okay, that's all for chapter 8. Okay, so we're going to look at chapter 9 next. Okay, this says green chemists prevent all kinds of catastrophes. So we're going to talk about alkynes next. This is chapter 9. Okay, in the opening photo here, okay, there's a structure here that contains two alkyne groups, two triple bonds. This is a toxin that occurs in the skin of this particular frog. Alkynes contain a triple bond. Their general formula is CnH2n-2. Okay, so to go from a single bond to a triple bond, we lose 4 hydrogens. So there are 2 elements of unsaturation for each triple bond. Okay, there are some reactions of alkynes that resemble the reactions of alkenes. Okay, like addition and oxidation. Okay, we'll see some other reactions that are specific to alkynes. Okay, in terms of nomenclature, by the IUPAC, you find the longest chain containing the triple bond, okay, if the alkyne is the principal functional group. And the suffix will be changed from ANE to YNE. Right. We'll number the chain starting at the end closest to the triple bond. Okay, we'll give branches or other substituents a number to locate their positions. Okay, so here we have 4 carbons. Triple bond is between 1 and 2. And so this is called but-1-ine. And it is a terminal alkyne. The triple bond's at the end of a chain. A terminal alkyne has an acetylenic hydrogen, okay, which we'll talk about shortly. But-2-ine, okay, we've changed the position of the double bond, is an internal alkyne, and there are no acetylenic hydrogens. All right, all other functional groups except ethers and halides have higher priority than alkynes. Okay, this is more a commercial issue rather than a chemistry laboratory issue, but well, there are some alkynes, I won't say many. Some of them are still widely known by their common names. Okay, so this is propyne, and it's commonly called methyl acetylene. Okay, this part of it is acetylene. And then this one could be called isobutyl. Here's an isobutyl group, isopropyl acetylene. This is the acetylene group here. And the simplest alkyne, H, C triple bond H, is commercially called acetylene. Okay, in terms of physical properties, alkynes are nonpolar, okay, like alkenes and alkanes. They're insoluble in water. They are soluble in most organic solvents. Their boiling points are similar to alkanes of similar size. They're less dense in water. Okay, that reflects the fact that they're associated by London dispersion forces, which are weaker than hydrogen bonds in water, so they, on average, they're not as close to each other. And up, excuse me, up to 4 carbons, they are gases at room temperature. All right, ethine is commonly called acetylene. It is used in welding torches. Acetylene in the air actually burns with a yellow, dirty, sooty flame. And so when it's used in welding and cutting torches, it's first mixed with oxygen. And the oxyacetylene flame reaches temperatures as high as 2,800 degrees Celsius. Okay, there's a lot of energy that's stored in that triple bond. So there's a lot of heat that's released when acetylene undergoes combustion. Okay, it is thermodynamically unstable. Okay, when it decomposes to its elements, it releases 234 kilojoules of energy per mole. All right, so so an acetylene tank will contain a preservative, okay, to prolong the shelf life of the acetylene in it. All right, acetylene. Acetylene can be synthesized from coal. If you use calcium carbide, and you add water to it, that produces acetylene plus calcium hydroxide. Okay, so we heat coke, which is crude carbon, coal with lime, which is calcium oxide, and electric furnace to form the calcium carbide. Okay, and then drip water on the calcium carbide to form acetylene. Okay, back in the 1800s and early 1900s, they had what were called carbide lanterns, okay, where you took calcium carbide and dripped water on it. That produces acetylene, which was then burned to produce a lamp. Acetylene can also be produced from natural gas. If two molecules of methane are heated at 1500 degrees Celsius, okay, we get dehydrogenation. 3 equivalents of hydrogen are released, and acetylene is a byproduct. Okay, and this reaction takes place very quickly. Right, let's look at the molecular structure of acetylene next. Okay, the hybridization of the carbons is sp. A sigma bond is formed between the carbons by overlap of their sp orbitals. Okay, the sigma bonds to the hydrogens are formed also by using sp orbitals. Okay, since sp orbitals are linear, acetylene will be a linear molecule. All right, each carbon then has 2 unhybridized p orbitals, and they're perpendicular to each other. They're 90 degrees apart from each other. And these unhybridized p orbitals will overlap to form 2 pi bonds. The electron density, the pi electron density, is actually cylindrical around acetylene. Okay, so here's the electron paramagnetic map. Okay, around the hydrogens, you have low electron density. In the region of the pi bonds, it's high electron density. Okay, this is key to the reactivity both of the acetylenic hydrogens and to the pi system. Okay, the electron density. Okay, a triple bond is stronger and shorter than double bonds or single bonds, and that's illustrated here using ethane, ethene, and comparing those to ethine. Also, the CH bond in ethine is a little bit shorter than in ethene or ethane. Okay, hydrocarbons are not notoriously acidic. Okay, in fact, they are very unacidic. Okay, so here we have ethane, and the conjugate base would be CH3CH2 minus. pKa is about 50. Okay, so the Ka is like 10 to the minus 50th power, so it's an extremely weak acid. Okay, not much difference with the alkene. Its pKa is about 44. And then if we look at the alkyne, its pKa is about 25. So it's significantly more acidic than the alkene or alkane. Okay, it is less acidic though than water or alcohols. Water is 15.7, alcohols are about 16 to 18. Okay, but right above acetylene, we have ammonia. Ammonia is a weaker acid than acetylene. Okay, so that means that the conjugate base of ammonia, NH2 minus, is a stronger base than the acetylide ion. Okay, so that's going to be useful as far as synthesis reactions. Okay, so terminal alkynes are more acidic than other hydrocarbons due to the higher S character. Okay, if the hybridization is SP, the S character is 50%. For an SP3, the S character is 25%. You got one S and three P's, so 25%. Terminal alkynes can be deprotonated quantitatively with strong bases such as sodium amide, NH2-. That's the conjugate base of ammonia. Hydroxide and alkoxide bases are not strong enough to deprotonate the alkyne quantitatively. Okay, so starting with but1-ine, which has an acetylenic hydrogen, and reacting it with sodium amide. And this is usually done in liquid ammonia. Ammonia is a gas at room temperature, but if you cool it, off the top of my head, the boiling point is something like minus 38 Celsius. Okay, so if you cool it enough, it becomes a liquid. Okay, so we have an acid-base reaction that goes to completion. Okay, so NH2- takes this hydrogen, we get the sodium salt of this acetylide, and then when NH2 gains a proton, it becomes ammonia. Okay, this works because you can see the pKa of ammonia is 36, pKa of but1-ine is 25. So stronger acid to weaker acid, okay, will favor products. Okay, and then here's another example. This is cyclohexylacetylene. Okay, that's also deprotonated by NaNH2. Okay, but but2-ine does not have one of these acetylenic hydrogens. And so if you try to react it with NaNH2, there's no reaction. Right, these hydrogens are on an alkane. So back up a couple slides here. Okay, their pKa values are going to be around that of most alkanes, roughly 50. Okay, so with this last one, nothing happens. These hydrogens are not acidic enough. Okay, this talks about one of the ways sodium amide or sodamide can be prepared. It can be prepared from sodium metal and iron-3 catalyst. Produces hydrogen gas as a byproduct. And then this can be used to deprotonate terminal alkynes. Okay, so why do you want an acetylide anion? They're very good nucleophiles, so they can be used in substitution reactions, for example, and we can lengthen a carbon chain with an acetylide ion. Okay, here's a good example. Okay, so we've produced this this acetylide ion, and we reacting with iodomethane. We do an SN2, and then we lengthen the chain. Okay, so this is a good way of building longer carbon chains. Okay, it is an SN2, and okay, the substrate here, okay, really has to be primary or methyl. Okay, if you have a secondary or tertiary halide, E2 is going to happen. You get the alkene, not the substitution product. Okay, so this has to be an unhindered alkyl halide, methyl or primary. Okay, and that's exactly what this shows. Okay, if we use a secondary halide, okay, what happens is this will take a beta hydrogen, and we'll get the E2 elimination product. Okay, when this takes the hydrogen, you'll get the but1-ine. Okay, so this gained a hydrogen. Okay, so these are also strong bases. So if we can't do an SN2, then an E2 occurs. Okay, if we start with acetylene, or ethine, okay, it turns out that we can deprotonate this one side at a time. And so we can introduce two different groups. Okay, so here we're using NaNH2. Okay, that deprotonates this. This will do an SN2. And we'll add a 6-carbon chain to one side of that. Okay, we can deprotonate it again. And this time using bromoethane, we add 2 carbons to the other side. Okay, so this becomes dec3-ine. Okay, so again, we can add 2 different groups if we wanted to, starting with acetylene. All right, another reaction that we can do with these acetylide ions is we can use them to attack carbonyls. Okay, specifically aldehydes and ketones. Okay, this carbonyl group has a large dipole moment, so the carbon is partially positive. So the nucleophile then attacks, that pushes a pair of electrons up onto the oxygen, making it negative. And then we add water or dilute acid, hydronium ion, and O- picks up an H, and then we get an alcohol. Okay, this is done at 2 separate steps because, of course, if it weren't, the nucleophile would simply pick up an H, and that would be the end of it. Okay, so here's the general reaction. Okay, if we start with an acetylide, and we react it with an aldehyde or ketone, okay, this adds, and then when this reaction is complete, we add dilute acid, and then we get an acetylenic alcohol. Okay, besides the SN2 reaction, this is another way of lengthening a carbon chain. Okay, we'll look at alcohols in a future chapter. Alcohols are probably one of the most versatile functional groups. There's so many different ways to prepare them, and then there's so many different things you can do with an alcohol. Okay, so this produces an acetylenic alcohol. Okay, you can also do this with an aldehyde, and that produces a secondary acetylenic alcohol. It's secondary because this carbon is directly bonded to 2 other carbons and a hydrogen. Okay, so here's a specific example. We start out with 3-methyl-but1-ine. Okay, we pull off this hydrogen. pH, again, is a benzene ring. So we have an aldehyde group attached to a benzene ring, benzaldehyde. Okay, this then attacks the carbonyl. And when this reaction is done, then we protonate. Okay, so we've added this group, and we get a secondary acetylenic alcohol. Okay, the IUPAC name for this is 4-methyl-1-phenol-pent-2-ine-1-ol. Okay, we haven't really learned how to name alcohols yet. The alcohol does take priority, so it's the final suffix. Notice we dropped the E from the YNE suffix because the next letter is a vowel. Okay, if we start with a ketone, the product is a tertiary alcohol. Okay, so here we have cyclohexanone. Okay, so this will attack, we protonate, and we get 1-ethynyl cyclohexanol. Okay, the alkyne is a substituent, the alcohol is the principal functional group. Okay, so how would you make this? Okay, so working backwards, it would be most logical to disconnect between this alkyne carbon and the CH. Okay, disconnect here. And we would use, we would start with a but 1 on. Okay, we deprotonate that, and then here we would, working backwards, we would convert this to the aldehyde. Okay, so this attacks the carbonyl. Okay, it gives us a CO single bond, and then we protonate that to give the alcohol of the desired product. Okay, now we're going to change to a little bit different subject. We'll talk about synthesis of alkynes by elimination reactions. Okay, this is one of the usual methods of making alkynes. Okay, industrially, we saw that we could make acetylene from either coal or natural gas. And of course, acetylene is readily available commercially. We can do a double dehydrohalogenation, that is removal of 2 molecules of HX from vicinal or geminal dihalides. We can do dehydrohalogenation of a geminal or vicinal dihalide to give a vinyl halide. And under strongly basic conditions, a second dehydrohalogenation may occur to form an alkyne. Okay, so this is what is meant by a vicinal dihalide. Okay, we have 2 halogens on adjacent carbons. Okay, this is what we had in lab last week. For the first reaction, we made a vicinal dihalide. And if those carbons also have hydrogens, we can do a double dehydrohalogenation with a strong base. Okay, so we do a E2 elimination to form the alkene. We do another E2 elimination to form the alkyne. Okay, the first dehydrohalogenation, of course, is faster. The second one is slower. Here we have a geminal dihalide. Again, we do 2 E2 eliminations. Okay, the conditions that we use, you can use molten KOH. Okay, so take KOH pellets and you heat them to about 200 degrees Celsius so that they melt. It's also called fused KOH. Or you can do alcoholic KOH, KOH dissolved in ethanol at 200 degrees. That's going to favor an internal alkyne. Okay, sodium amide, which is a much stronger base at 150 degrees Celsius, okay, followed by water, favors a terminal alkyne. Okay, so here we have 2,3-dibromopentane, which is a vicinal dihalide. using fused KOH at 200 degrees. Okay, we have a double dehydrohalogenation, and this gives us the more stable internal, more highly substituted alkyne, which is pent-2-ine. Okay. Next, we're going to look at addition reactions. Okay, these are similar to the addition reactions of alkenes. The pi bond becomes 2 sigma bonds. Okay, the addition is usually exothermic because the sigma bonds are stronger than the pi bond. And 1 or 2 molecules may add. Okay, so here's the general reaction. So AB adds to the alkyne to give us an alkene. And then another AB could also add to give us the alkane. Okay, so one example is catalytic hydrogenation. Okay, we saw that we could convert alkenes into alkanes using hydrogen and a nickel, palladium, or platinum catalyst. Okay, using 2 equivalents of hydrogen, we can produce an alkane from an alkyne. Okay, under these conditions, the alkyne will be completely reduced. Okay, the alkene intermediate, where we add just 1 equivalent of hydrogen, cannot be isolated. So this goes all the way to the alkane. Okay, what if we don't want it to go all the way to the alkane? Okay, one way is to use what is called Lindlar's catalyst. Lindlar's catalyst uses palladium with barium sulfate, with quinoline, and methanol. Okay, going back to the previous slide, nickel, palladium, or platinum, okay, those catalysts are so efficient that they'll take it all the way to the alkane. Okay, if we use a catalyst which is not as efficient, then we can stop at just 1 hydrogenation. Okay, so what we've done here, barium sulfate is a very insoluble salt. Okay, it just serves as a diluent. It dilutes the palladium. Quinoline binds to various sites along the surface of the palladium. Okay, so it reduces the number of available sites. The quinoline takes up a lot of space, so it blocks several of the available sites. And so we say the catalyst is partially poisoned. Okay, this reaction occurs selectively with cis stereochemistry. Okay, so starting from the alkyne, we add 1 equivalent of hydrogen, and our product is the cis isomer. Okay, this takes place at the surface of the catalyst. Okay, both substrates, the hydrogen and the alkyne, have to be absorbed on the catalyst for the reaction to occur. Once absorbed, the hydrogens add to the same side of the double bond. Okay, and that's why we get the cis. Okay, if we want the transalkene, there's a different method that we can use, and this is what's called the dissolving metal method with metal ammonia, and I'll talk about that in more detail on Wednesday. So I'm going to go ahead and stop here,
textbook?
The textbook, the hardcover textbook.
Okay.
Yeah.
And are we doing the macro scale or the micro scale version?
Most likely the macro scale, unless we're short on material. I think we'll have enough MCPVA. We'll have to check our supply of that.